n being.
Yeah, it's strange because here is V lambda, here is V lambda. So we took C lambda mu from the definition of V lambda. I mean,
Yeah, so.
They're just arbitrary, or we will compute them later, or what?
Yes, so actually, well, not to. So you can think that C lambda mu is 1 for all lambda and mu. But in principle, there are some degenerate situations where some of them are 0. And so then if they are, so 0 are, well, gives a different structure of vertex operators, but you can just forget about them and just put them on. Mm-hmm. Только сделать где? So,
вот у нас есть алгебра, вектор, если двух n z.
А
вот хочется, так, не знаю, что-нибудь типа i z или i на какой-то константу z, типа тоже
Нет, так не получится. So the problem is going to be that then you need series with powers of z being complex number. It's not clear what should it mean. Well, actually, so.
Когда мы начинаем что-то вводить двух операторов, то там все окей. И в квадрате
You mean
не, ну я просто пытаюсь, я просто что-то слышал, что когда бывает нужна решетка уже неодномерная, бывает нужна пересигнатура. Можно решить тем, что тоже делать.
Well, I'm not sure about complex numbers.
То есть это просто, типа, например, то же самое, что взять вместо n вместо натурального отрицательного.
So I think it's important that that these numbers are, so the let's see. I think it's important that the pairing of a number with itself should be positive. I can't say right now where is it used, but it seems to me that you'll have problems with associativity otherwise.
Я слышал, что как раз именно для этого делают индекс, когда пытаются какую-то гамма-систему реализовать, и гамма реализует как раз эффект определенного.
So let me see where it may be important. Let's see. Okay, maybe we'll get there. So I wonder what's going to be with the v lambda z v mu of z. So what's the power would be needed to make it 0? If you take the imaginary numbers there. But okay, maybe when we get here, we can check. Okay? Что-то какие-то у меня сомнения. Okay, so да. And so what's going to be OP? Okay. But what's going to be the commutator? So for example, if you write lambda and lambda, yes, then you get here lambda squared, which might be negative. But what would be, what then you can say about the commutator? Yeah, but is it possible to say that they are local with each other? So I mean, if you have, so I mean, you have two options. So you may have here say 2, or you can have here z minus w minus 2. So you're saying that the commutator is local in both cases, or what? But can you check it? So, there should be some difference, right? Yeah. Okay. So let's see. So first of all, is it clear what's written here? Maybe let us do one small check.
Sorry.
Yes. Yes. Yes, we did. We had such a formula in the context of boson fermion correspondence. So let us make a computation. So if we take v lambda z and apply it to mu. So what are we getting?
Just want to check that
And
this formula gives us what?
just to see how it works. So I apply it to mu and take the matrix coefficient in front of lambda plus mu. So what am I getting? So first of all, you can see that this is just 1, right? If we apply this to the high state vector, then we get just 1. Okay? And so this somehow makes shifts. Yeah, but after that we want to apply S lambda, so we also want to take just a unit from here. Yes. So Z2, what's the power? Should depend on mu somehow. I would say lambda mu. What do you think? So let's compare with this formula. Yeah, so our n is going to be minus lambda square over 2 minus lambda mu, right? So the n here. And then we put this n here, and we get exactly lambda mu. Okay? So we want to apply v lambda of z to the high state vector. And then we are looking at, so this v lambda of z is such an expression. And then we apply each coefficient separately. Okay, and now if n is such a number, then we get this lambda plus mu. Okay? Good. Now if n is such a number, what is the power of w here? Just lambda mu. Yeah, because lambda squared over 2 cancels, and the remaining things, and that's exactly the lambda mu there. Okay? Good. So at least this agrees. And one more remark. Says that if v lambda z are pairwise local, and local with h of z, then yes.
I mean, we decided not to just arbitrarily.
Absolutely. Absolutely. Then we are getting this VOA structure on v z square root of n. So is it clear, or? Sorry? Mm-hmm. So Mike.
Давайте сейчас после ума я посмотрел, но проблем нет. Ну, давайте лучше после.
Mm-hmm. Mm-hmm.
Sorry.
Yeah.
Proof that lambda should be expression of such kind.
No.
Or what? We just
No.
write.
So the claim is, so I made one remark and I'm about to write the second remark. Maybe let me write it. So the formulas and determine V lambda of W unique. Okay? So whenever we have some formula satisfying these two conditions, of course we better check it for this formula. So then V lambda is completely determined. Okay? Say it again? Yes, thank you. Mm-hmm. So this is the second part, and what about the first remark? By the way, please raise your hand if the second remark is clear for you. Okay, then let's discuss it. Anfisa, can you explain why? In a sense, yes. Mm-hmm. So here, once again, so what do we know? We know that you have V lambda of Z, which somehow, so let me draw it, pi lambda, pi mu, and pi lambda plus mu. So we have this operator, V lambda whatsoever minus lambda squared over 2 minus lambda mu. Okay? And all these guys, they are mapped to 0. Okay? Now if I want to compute how to map this vector, then I have a commutation relation saying that if I go here and then there, then this is the well, or minus I go here and there, so the difference is V lambda of W. So I only need the operators to know, maybe it's not completely correct, yeah, I also need to know what is these operators.
What is the
So we have this high state vector, And then we have the operators which act v lambda something, mapping this vector to somewhere here.
So we need v lambda n, yes?
Yes, yes. Applied to mu. And maybe indeed for these commutators are not enough. Yeah. Maybe this is. Mm-hmm. Yes. Then we can use the commutators with positive ends. Yes, so I mean, if we want to compute this, and we act somewhere upstairs, is the same as, well, commutator is going upstairs and then here. So actually we had such a reasoning with the boson-fermion correspondence. But just what I want to say, that if this is true and this is true, then we are done. So shall we elaborate on this in more details or not?
I suppose you should somehow use something quite non-degeneracy of the scalar product in
Mm-hmm. Yes.
but I didn't understand how this consideration where we use it.
You see, so we, first of all, let us,
In this picture.
let us first determine what is the v lambda n applied to mu. So if you apply to this h n with n positive, so then this is going to be well, up to lambda. So the hn acting on mu is 0. Therefore, maybe I should write here m. This is up to lambda, lambda v, lambda n plus m mu. Do you agree? Say again?
I mean the quotation relation. Don't we need
Yes, so this W gives the shift. Okay? So therefore, such a vector, well, using induction, yes, we know for such a vector how the positive h's act on it. And if we know this, then we are done. Okay? Good. So the second remark is fine, yeah? What about the first remark?
We just know that if generators somehow local, then any expressions which we obtain from the generators by normal ordering and taking derivatives are pairwise local. So
Yeah, so this is the reconstruction theorem, yeah? So the only thing which we have to explain is why the Fourier modes of these guys and h of z generate a whole space. Uh-huh.
In this remark, we already suppose that V lambda of E is
Not really. So I mean, whenever it exists, and so whenever there is, we are able to define the operators V lambda of Z such that they are
local.
with itself and with H of Z, and they satisfy all the kind of properties compatible with degrees and so on, then it's okay. So you remember we have this, so we have the reconstruction theorem. Saying that if there are some vectors, I don't know, A1, A2, so on, such that the Fourier coefficients of y, a, k, z generate the whole space from the vacuum vector. So then we have the VOA structure will provide it locality. Locality, and there are some other minor properties like YAKZ0 is AK plus. And so the suggestion is to take these A's to be vacuum vectors, lambdas, and H minus 1. Yes, yes, yes.
So know that lambda 0 maps vacuum to the highest vector of pi lambda. Yes.
Uh-huh. Mm-hmm.
And for pi lambda, I think that algebra generates. No, sorry. I think the algebra generates pi lambda from
Yes.
this vector.
Mm-hmm. 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 But by the way, it's not 0, but minus lambda squared over 2. Right? Okay, so we can, starting from the vacuum vector, we can get all other vacuums by applying Fourier coefficients of our V lambdas. And from these vacuums, we can get the whole thing.
So is it integer minus lambda squared?
It is.
Because it's integer.
Yes, exactly. Exactly.
So here will be
Absolutely. Yeah.
So for mod n, the consideration the same for this moment, and there we should use something like reconstruction version of reconstruction theorem or super
Yes.
theory.
Yes. Absolutely. So let me ask once again the question. So about these two remarks. So have we digested them enough, or we have to discuss a bit more? Because actually these are the most important ingredients of the proof. So you somehow first give a formula satisfying the conditions we need to satisfy, and then afterwards you somehow check the locality. So we will leave the proof of the locality for the exam, but at least I hope you understand why do we need this and why they are interesting. V lambda with B mu and V lambda with H. Well, I'm happy to understand that you know this. Yeah. Okay. So okay. So maybe let's check at least something. Let's check for this expression. So can you tell me what is T commutator with V lambda Z? So in order to check that something is a vertex separated algebra, apart from checking locality, we also need to incorporate the derivation, right? And then we need to know what is the commutator of T with V lambda. Why? This we have computed it somewhere. I mean, this is what we want to have. Yeah. The goal is to check that this explicit formula, this one, does satisfy this property. So the answer indeed should be lambda times the normal ordering. But is it true? No, but no, we don't know this. So this has to be proved anyway. Yeah. Well, so in principle we can, but I think it's easier to commute T with these guys. Where?
Экспонент.
Oops. Thank you.
Вот этот экспонент можно показать.
Mhm.
How
Okay. Is it true?
Давайте напишем так. Экспонента напишем z в степени n умножить на какой-нибудь оператор.
Yeah, but how to write so we want to take t with the product of commutator with the product of exponents. So how to compute t with the exp of something?
Потому что да, d с n это h n
Mhm.
maybe we can
или с n.
Let's see.
we can write exponents as somehow, I don't know, x of minus lambda h minus of z, x of h plus of z. These expressions will be like commutative, and we know that on this h plus and h minus commutator with t will be act as derivative. And then by Leibniz rule we will have that on the ordered exponent we will act as derivative.
Mhm. Okay, maybe let us make the following. So what do we want to prove? So we want to prove that this is lambda h of z v lambda of z, right? This is what we want to prove, yes? So this is going to, again to be your problem in the exam. Okay? But at least, so I just want to stress that we do need to check this. Yes, so in order our vertex space algebra to become formal, we need a operator T satisfying such a condition. Okay? And the reason why this should be true is given here. Okay. Now let me do several more conceptual general things. Let me say the following lemma. So each pi lambda is a pi m square root of n is a module for pi 0. So I claim that so in our vertex separated algebra is a direct sum of a vertex separated algebra pi 0 and its modules. Some questions or?
The question is, for what we prove this formula, which we
Which this formula? So what is the operator T? So what kind of properties does it have? So absolutely, yes.
Yes, but why we need this formula?
Because so what is the operator T? Yes, so it is some operator on, just by definition, what is the derivation on what is the conformal vertex separated algebra. You need operator T satisfying some properties. And one way to formulate this property is this one. Okay? So another variant is to write a commutator, but this is one way to define it. And then our T, yeah, say it again?
We somehow used it.
No, we're not using it, but we are saying that this T, which is defined in a very explicit way, yes, is L minus 1, which is the sum H n minus 1 minus n, yes? This T does satisfy this property together with V lambda given by the explicit formula. No, it's actually, this is a thing which is very understandable, so you don't have to skip it. So we have such a formula. Yeah?
I understand why if we assume that there is a structure of vertex separator algebra, this all is true.
Yes.
I'm just a bit confused in which statements which assumptions in which statements we assume.
So there are no assumptions there. So this is just a general nonsense, just a general theory of vertex separator.
One of Z is supposed to exist. We didn't.
Как бы, давайте так, у нас есть вероятность иногда алгебра, у нее есть.
Yes.
В том числе, то есть мы хотим доказать, что у нас есть вероятность. В том числе вероятность алгебра есть аксиома существования там Т, который...
Да, и вот это
Вот ему, вот мы
если
написали, что если оно
есть,
есть, причем что оно есть, то оно должно быть существовать. Это как бы, ну, в общем, в принципе, если какой-то оператор.
можно еще вот так сказать, что мы написали эту формулу, и можно сказать, как оно выглядело, если оно существовало. А кстати, мы написали формулу, и вот оно такое. Просто это не помогло нам ничего выяснить.
Это помогло нам выяснить, что мы проверили одну из аксиом вертексной оператора на. Мы проверили, что есть ТВЦ, что ТВЦ проверяет аксиом вертексной оператора на.
То есть мы не проверили, мы оставили это на экзамен проверять.
Ну, мы сделали все, что можно проверить.
Ага. No, you're absolutely right. We did not check this formula so far. So the exam problem would be to substitute V lambda from there and T by this explicit formula and check that this is true.
Посмотреть, чего нам ожидать, как оно должно быть.
Okay. Now what about the lemma? Is it clear what's stated and why it's true?
It's very clear. Direct sum of, sorry,
It's a direct sum of modules of pi 0. We can actually write.
Models of pi zero как вероятность.
Mhm.
Сейчас, надо вспомнить, что сейчас модули вертекс алгебры, там, значит, там вам
Yes.
не надо, а что там надо,
So please, yeah, it's a good question. Please raise your hand if you remember what is a module over a vertex separator algebra. Because we briefly mentioned this 3 weeks ago, but it was kind of 3 weeks ago.
там что-то надо, чтобы оператор коммутирует.
Then let us. Right. Yeah, absolutely. Exactly the definition. So we have V, which is our vertex separator algebra, and we have M, which is a vector space, and we have Ym of AZ. A is from V. These are fields on M. Okay? Good? On M. Not on V, but on M. And then what were the conditions? So they were, of course, local, which we somehow...
Their commutation relations.
Yeah, so we wrote Ym of AZ, Ym of BW, yes? Ym of BW ym of AZ. And what was the third series? What should I write?
What's the sum of ym of am is w divided by z minus w in n plus 1.
So how can we read it? Write it in a more. See?
There should be
Yeah, we should apply to a vector, but how to write it in a short form?
This y of a z minus w.
Okay.
Yes.
Okay.
And then indeed, as Kosti is saying, we better apply it to, well, maybe I should not see here, but I don't know. Because A and B are elements from vertex separated algebra, and here we apply it to an element from V. Yeah, so I don't know, what from M. So maybe I put here gamma. And so these guys, they have to be expansions of one and the same thing. So in particular, this implies the locality and so on. But so these are kind of standard stuff, but for modules, not for algebra itself.
But here we have some kind of special situation when we have subalgebra of it.
Absolutely.
And vacuum representation just is the sum of modules.
Right.
And we don't have to check on this condition. So we have to check only closeness of submodules.
Yes. Okay. So actually, you see, this is a very special case. I think, Andrei, you asked this at some point, if we can glue something from a larger vertex separated algebra from smaller ones. Yes, you asked about several vertex separated algebras, but here the situation is a bit different, but still. So you have a small algebra, which is the Heisenberg algebra. And then you take kind of semi-direct product with its modules. Yeah, so such a construction somehow is familiar in algebra. And here, but you see, it's absolutely not kind of not a free statement, yeah, not an evidence statement. Because of course you have modules and you have actions of your vertex separated algebra on these, but you also need fields corresponding to your elements from your modules. And these fields, they have to act on everything. So this is really very rich structure, very rich interaction. Yeah.
Даже любой набор, просто любую прямую сумму из фоковских модулей. Вообще, давайте любой фоковский модуль сам по себе является представлением алгебры, вертексной алгебры без инверта.
Any Fock module. Well, you see, I'll say, any Fock module is isomorphic to pi 0. So, in a sense, Yes, so I mean, depends on what you really want. So I mean, different Fock modules are isomorphic as vector spaces.
Я имею в виду, что вот есть... Нет, ну, как бы, то есть вот этот модуль, который вы сказали, что вот веб-ориентированный она является модулем на вертексной алгебре, которая гейзенберговская обычно, да? Но на самом деле она тут даже написано, что она прямая сумма. Да, прямая сумма одинаковых модулей вертексной алгебры.
Over P0.
А вот то, что мы взяли именно таким, мы взяли.
But so you see, it's a bit delicate thing. So I mean, here these models are not isomorphic because you see they are living on different levels, and this actually makes some difference. So it depends on what they mean by isomorphic, but so in fact they are somewhat different, and H naught acts differently. I don't think so. Yeah.
Конечно, нельзя. Даже отсюда можно выкинуть половину. Вот, выкинуть какой-нибудь веб-корень из двух, а веб-корень из двух оставить, веб-корень из двух. Два корня.
Well, there might be some trivial way to extend it. Say, you probably might say, I don't know, you might say that all the fields corresponding to the module are just 0. I don't know if it should work. Oh, no, this should not work. No, I don't know. Problem. Okay, so this is the first thing. And now I also want maybe to close with another conceptual thing. So another conceptual thing is a generalization to so higher dimensional generalization. So namely, assume they have L, which is the lattice in R, well, let's say R to some n. Okay, and we assume that yes, so Rn of, let me put V, and V is equipped. Yeah, it's a good idea, but what? Okay, with a scalar product, and L1, L2 is an integer. Может, и можно. Но я думаю, что надо приговаривать какие-то слова. Я так думаю. Но может и не нужно. for any L1, L2 from L. And then we organize H, HL. Maybe what should be the notation? Well, okay, let me just write it as L tensor C. So for example, in our one-dimensional case, this was just one-dimensional Heisenberg algebra, and this is the what is called Heisenberg algebra of larger dimension. No, just to be a vector over Z even maybe, because this is the L is not a vector space, yes, but it's a lattice. Just a complex vector space. So in a one-dimensional situation, you get just your one-dimensional Heisenberg algebra. Okay, and then we take the maybe I'm going to use H here, and then you take H tensor TT inverse plus center, one-dimensional center. And as usual, you say that ht to the k, ht to the n equals to h1, h2, delta k plus n 0, k, and h1, h2. Okay? So this is the formula. The only difference is that now the algebra is not one-dimensional as we used to, but can be higher dimension. So you see in particular, so an example, so if L is just square root mz, as we had before, then H has a basis H m or Hn corresponding to this number n. Okay? Good? Okay. So what else I want to say? What else I want to say? So in general, for example, if L is of dimension 2, say, I don't know, whatever, square root of mz plus square root of mz, say, twice the same. Then H has a basis H m1 n1 and 2. Yes, so the algebra is higher dimension. The Heisenberg algebra. Well, if we want scalar product to be in Z, then yes. But of course, there might be some other examples. So it's not the only example of such a lattice. It depends on how you, okay, so it depends on how you define it, yes. We can write m1 and m2 if these are orthogonal vectors, right? Okay. Good. By the way, this is a bad way of writing. Maybe it's better to write LC. So it's not actually the tensor product. Yes, you can see that here L is just a discrete thing, right? And then for each such a element from L, we take a copy of complex space. Okay? Say again?
I suggest it's much better because I wasn't quite.
Yeah. So it's kind of complexification. Yes. So you attach to each element of the lattice, you attach the. No. Wait. Sorry. No. Nothing. So. Yes. So. Just I skip. I H hat. So this is H hat. Okay. Good. Okay, and then just wanted to say that you can still organize, so just like a theorem. Maybe I should also say that for lambda in H, one can define a Fock module by lambda such that H, there exists a high state vector in pi lambda, and H positive lambda is 0, H 0 lambda is H lambda times lambda. And the whole module is the symmetric algebra of H tensor C of t inverse. Applied to. Yes. H is an element from H.
Should lambda be the lattice itself, or it should be in H?
Lambda can be, in principle, any vector in H. But to construct vertex separated algebra, we take it from the lattice. And the theorem says that we can organize the direct sum over elements L from L by L, and this has a vertex separated algebra structure.
Фишка в том, что может быть это не всегда такая сумма каких-то двух вероятностей. Например, может быть эта решетка, там, часть какой-нибудь решетки корней.
So this is some lattice. But in order to be vertex separated algebra, we need some condition for it to be even. It's exactly to make it true vertex separated algebra, not super vertex separated algebra.
Is there any interesting particular cases when lattice is like weights of characters for simple algebra?
Yes, it can be a root lattice for Lie algebra. For example, we've seen an example of SL2 hat, but you can take, and this corresponds to the root lattice for SL2.
So then we to have this structure of what? The representation of this VOA of, I don't know, this VOA is the same as VOA which we
Isolation on level 1.
Ага,
Если
yes,
взять
yes.
сейчас, надо взять да, ну, в смысле, сейчас надо взять, сейчас, ну, в смысле, вот, например, для SL2,
Мгм.
там же, ну, как, ну, скачивать себе, если мы возьмем решетку с шагом корень из двух, мы получим представить на уровне.
Мгм.
А вот если мы возьмем шагом корень из трех, то мы не получим представить.
Да, правильно.
Корень
правильно.
из двух это как раз тоже.
Ну да, то есть,
Мгм. Да.
ну и корень из трех, можно сказать, ну, плохо. Корень из трех в квадрате это 3, а надо, чтобы было
Мгм.
целое, ну,
Мгм.
хорошо. Корень из четырех, вот, вот, тоже подойдет.
Не подойдет.
То есть так можно рисовать только Vertex операционной алгебры для там, какой-то финной алгебры, которая была бы на уровне 1.
На уровне 1, да.
Больше не.
Ну вот прямо так, только на уровне 1. Окей, проблема. Ага. Да, конечно.
А есть какие-нибудь еще какие-нибудь утверждения в духе того, что там, не знаю. Ну, я так понял, что вот эти решеточная алгебра, она там такая самая важная, в смысле, любую другую, ну, очень многие можно строить с помощью нее.
Мгм.
Есть какая-нибудь там теорема в духе, вот любую можно построить?
Нет.
Да, в смысле, есть какие-то контрпримеры явные или...
Ну, понимаете, утверждение уж больно неявное, поэтому значит, любую можно построить. Так это не скажут. Мгм. Мгм. Многие можно.
Такая очень конструктивная наука, это, с одной стороны,
Да.
прикольно, с другой стороны,
Да. So, any further questions? Okay, so if not, let's stop for today. And don't forget that next time we're going to have an exam. So as usual, it's going to be here, it's going to be offline, it's going to be at the usual time. But if there are some reasons why you can't come, please write me and we'll decide.